Welcome back, everybody. So the goal for today's video is to talk about a theorem called the Monotone Convergence Theorem, which is a way to show that a sequence must converge. By the end of today, we should be able to give the definitions of some terms which are used to describe sequences, namely the terms monotone, increasing, decreasing, and bounded. We should be able to state the monotone convergence theorem. We should be able to determine whether a given sequence is monotone and or bounded, use the monotone convergence theorem to show that a sequence converges, and finally we should be able to find the limit of some recursively defined sequences. So to begin with, let's start by introducing today's set of terminology. The first word that I want to describe is the word increasing. A sequence is increasing if the terms increase in value as you move through the sequence. Each term in the sequence is greater than or equal to the previous term. So with every step in the sequence, we want to make sure that the value of the term is larger than the one that we had previously. So in symbolic notation, I would write a sub n, any term in the sequence, has to be greater than or equal to the previous term in the sequence, a sub n minus 1. Now corresponding to that, we have the definition decreasing. A sequence is decreasing if, can you anticipate what this definition is going to be? If each term in the sequence is less than or equal to the one before. Symbolically, we would say that a sub n, any arbitrary term in the sequence, has to be less than or equal to the one that came prior. Now, both increasing sequences and decreasing sequences are great and are necessary for the application of the monotone convergence theorem, which we will use in just a few minutes. So we have a collective term to describe that your sequence is either increasing or decreasing, and that word is monotone. A sequence is monotone if it either goes up consistently, it is increasing, or it goes down consistently, it is decreasing. In either one of those cases, if your sequence either goes consistently upward in value or consistently downward in value, the sequence is called monotone. Now the last bit of terminology that we're going to need in order to state and apply the monotone convergence theorem is the word bounded. A sequence is bounded if all the terms in the sequence have values between some two fixed extreme numbers. A sequence is bounded if every term in the sequence has a value between two fixed numbers. No matter what term in the sequence you take, you have to be able to squeeze that term between some maximum value and some minimum value. In this case, the sequence is called bounded. The values of the sequence are bounded between little m and capital M. So let's practice using these definitions. Let's have a look at a few sequences and see if we can decide what adjectives we can apply to them. For each of the following sequences, determine whether or not the sequence is monotone, so either increasing or decreasing, And then also let's determine whether or not the sequence is bounded. And in this case, we don't have to do a formal proof, we can just do some informal argumentation. Let's consider the sequence a sub n equals 1 over n. Now of course we cannot divide by 0, so let's just agree that the first term is going to be where n is equal to 1. Because n equals 0 would cause us to divide by 0, and that's not allowed. So let's perhaps create a visual representation of this sequence. Create a plot where I will put n on the horizontal axis, and I will put the value of the term on the vertical axis. Now when n is equal to 1, and I plug n equals 1 into this formula, I get 1 over 1, which is 1 itself. When n is equal to 2, I get 1 over 2, so 1/2. When n is equal to 3, of course we get 1 over 3, which is 1/3. And so if I plot the values of this sequence, dividing 1 by increasingly large numbers, I'm just going to continue to get these fractions. 1, 1/2, 1/3, 1/4, and so on. So the first thing that I'm going to note is that all the values in this sequence are going to have to be less than or equal to 1. Because I'm always dividing 1 by some number. Additionally, all the terms in this sequence are going to be greater than 0, because I'm always dividing 1 by a positive number. 1 divided by a positive number is still going to be positive. So all the values in this sequence are trapped between the constant 1 and the constant 0. As a result, I can safely conclude that this sequence is bounded. Now let's also try and figure out, both from our arithmetic and algebraic reasoning and from the graph, whether this sequence is monotone. Now every time we increase n by 1 unit and we move through the sequence, we are dividing 1 by something larger than what we had before. an, which is 1 over n, is always going to be less than or equal to 1 over n minus 1. Because you're dividing by something larger, the result is always going to be smaller. As a result of that, the sequence is definitely going to be decreasing. You can see this in the picture as well. As we graph more and more terms of the sequence, their output values are progressively declining. They're getting lower and lower as n increases. Since the sequence is decreasing, it must be monotone. Monotone meaning either decreasing or increasing. The sequence is decreasing in this case, so it must be monotone. Let's try it with the next sequence. We have the geometric sequence a sub n is equal to 2 to the power n. Let's see if we can decide whether the sequence is monotone and or bounded. Now if I graph a few terms in this sequence, n against an, when n is equal to 0, for example, the output is 1. When n is equal to 1, the output is 2. When n is equal to 2, the output is 4, and so on. We can see the graph growing in a shape very similar to an exponential function, because geometric sequences behave like exponential functions. Now from the graph, we can see that this sequence is increasing. Because the points on the graph are moving steadily upward as n increases. But we can also deduce this from the formula itself. If we take 2 to the n, and we take 2 to a large power, then you're going to get a larger result than if you took 2 to a smaller power. Because the sequence is increasing, the sequence must also be monotone. However, I think that this sequence is not bounded. In particular, the values of this sequence don't have any upper cap. As you take 2 to increasingly large powers, the value of an is just going to keep growing and growing and growing off to infinity. So this sequence is not bounded on the top. It keeps growing forever without limit. So this is not a bounded sequence. Let's consider the example an is equal to -1 to the power n divided by n. Once again, we'll let the first term be a sub 1. Now, let's go ahead and graph a few terms of this sequence. When n is equal to 1, for example, we have -1 to the power 1 divided by 1, which is -1. So that's down here. When n is equal to 2, then we have +1 over 2, so that's roughly speaking up here. When n is equal to 3, we have -1 to the power 3 over 3, which simplifies to -1/3. So that's back down here. So already I suspect that this sequence is not monotone. The sequence definitely cannot be decreasing, because moving from n equals 1 to n equals 2, the values went upward. However, moving from 2 to 3, the values went downward. Because these values went both up and down, this sequence is neither increasing nor decreasing. And because neither of those conditions is satisfied, we can safely conclude that the sequence is not monotone. Now, what do you think? Is the sequence bounded? Are all the values in the sequence trapped between two numbers? I think the answer to that question is yes, the sequence is bounded. There are a couple of different ways to see that. One is to think about the graph. This sequence of terms at its lowest has a value of -1 and bounces up to 1/2, down to -1/3, then up to 1/4, and so on. Over the course of time, it's just getting closer and closer to the n-axis. So from the graph, all the terms of the sequence seem to be bounded between -1 at their lowermost, and at the highest they reached 1/2. Because all the terms in the sequence are trapped between these two extremes, they're squeezed between these two output levels, the sequence is bounded. Now finally, let's try and have a look at this recursive sequence. They say to me, start with a0 equals 2, and for every subsequent term in the sequence, you can calculate the value by taking 1/2 of the previous term and then adding 3 to the result. So let's write out a few of the values of this sequence, and let's see what we might conclude. We're told that a0 is equal to 2, so a1 must be equal to 1/2 times 2 plus 3, which simplifies to 4. A2 is equal to 1/2 times 4 plus 3. 1/2 times 4 is 2 plus 3, so that's 5. A3 is equal to 1/2 5 plus 3 is equal to, I guess that's 2.5 plus 3, 5.5. And so on and so forth. A4 would be equal to 1/2 times 5.5 plus 3, which is equal to a little bit more than what we had before. I'm not going to go ahead and calculate that. So it appears, based on this pattern, that the sequence is increasing. Technically, the conclusion that we have made has not been supported by an airtight argument. You can't just calculate a couple of values of the sequence and conclude that all of the values in the entire infinite sequence must be increasing. However, since we were only asked to give an informal argument, the skeptic is on break. They are not going to come in and question our conclusion. This will be enough for our purposes right now. Therefore, I'm going to go ahead and conclude that since the sequence is increasing, that the sequence is monotone. So the next thing that I'm going to ask myself is this sequence bounded? So what I've gone ahead and done is I've gone ahead and calculated the values of a sub n for n equals 4, 5, 6, 7, and 8, so that we can perhaps begin to see a pattern. And it's looking to me like these terms in the sequence are getting closer and closer to 6, but never quite exceeding 6. Looking at all the terms from 0 up to A8, it also looks to me like this number is bounded below. It's never negative, so it's bounded below by 0, but in particular it always seems to be greater than or equal to 2. So by an informal argument, just by calculating several terms of the sequence and looking closely at them, I would conclude that 2 less than or equal to an less than or equal to 6. So the sequence is bounded. Now, if you're curious at all what a formal argument would look like to really prove that this sequence is increasing, no matter how many terms in the sequence you consider, to really prove that this sequence is bounded, the argument is quite beautiful, and it involves a technique which is called mathematical induction. Once again, that's something that is beyond the scope of the class right now, but if you have some curiosity about it, I've also posted an excerpt from a calculus text which goes through that calculation and that proof that this sequence actually is increasing and actually is bounded. That'll be posted to Canvas. So now that we've gotten some practice with that terminology, I would like to state our second theorem for the class. The first one was L'Hopital's rule for sequences, and the second one is Monotone Convergence Theorem. And both of these theorems so far are techniques that we can use to determine whether or not a sequence converges. Monotone Convergence Theorem says if, okay, so I'm about to give you the hypothesis of this theorem. If the sequence an is both monotone and bounded. All right, that's the hypothesis. In order to even use this theorem, you need to know for sure that your sequence is monotone and it is bounded. If those conditions are satisfied, then, here's the conclusion, the sequence must converge. So this gives you a tool that you can use in constructing a formal argument proving that the sequence that you're working with must converge to some limit. Exercise. Let's check out the following applications of the monotone convergence theorem, and let's check and see whether or not these uses of the theorem are logically valid or not. Here's the first use. Someone is inspecting the sequence a sub n equals 1 over n. We found on the previous page that this sequence is monotone, in particular decreasing, and it's also bounded. The values are always between 0 and 1. This person then concludes, by the monotone convergence theorem, that the sequence must converge. This use of monotone convergence theorem is valid. The first thing that this student checked was that the hypothesis of the monotone convergence theorem was satisfied. First thing that needed to be true was the sequence was monotone. The second thing was that the sequence was bounded. As soon as both of those things were true, the M.C.T, the monotone convergence theorem, was unlocked. And it was safe to conclude the conclusion of the monotone convergence theorem, which is that the sequence converges. No problems here. Okay, let's check out this second argument. The sequence a sub n equals 2 to the power n. We found that it was monotone, in particular it was increasing, but we found that it was not bounded, in particular it was not bounded on the top. So the student concludes that the sequence must diverge by the monotone convergence theorem. This use of the monotone convergence theorem is not valid. The student's answer is actually correct, in as much as this sequence 2 to the n really does diverge. But the student's argument, their rationale, their reasoning is flawed. So the skeptic is going to come in and is going to pick apart their logic to say, well, who knows if your answer is right, because I know for sure that your rationale is not valid. This student says the sequence is monotone, but the sequence is not bounded. Because the sequence isn't bounded, the hypothesis of the monotone convergence theorem is not completely satisfied. The hypothesis is that the sequence must be both monotone and it must be bounded. So that means that the M.C.T is still locked. Which means that even referring to the monotone convergence theorem is inappropriate. If this student wanted to argue why the sequence diverges, they're going to have to come up with different reasoning, different rationale than what they have used here. For the third example, the student says, hey, we had this sequence which was minus 1 to the n all over n. And we found that it was bounded between minus 1 and 1, or if you want to be a little bit tighter, between minus 1 and 1/2. However, the sequence was not monotone because the values in the sequence kept bouncing up and down. The student says, therefore, the sequence diverges by the monotone convergence theorem. Is this use of the monotone convergence theorem appropriate or not? This use is definitely not appropriate for the same reason as before. The sequence is not monotone. The sequence is not monotone, and therefore the hypothesis of the monotone convergence theorem isn't satisfied. So the theorem is still locked. And that means that even referring to the monotone convergence theorem, in this case, is completely inappropriate. Not a valid use. Not only that, but this time the student's answer is actually incorrect. One way to see this is to use a squeeze theorem argument. -1 to the n is always going to be equal to either -1 or it's going to be equal to +1, depending on whether n is an odd number or an even number. Which means if we divide that by n, the result is going to be squeezed between two fractions, which are going to 0 as n goes to infinity. So not only is this student's rationale incorrect, but their answer is also incorrect. So sort of a double whammy there. Now, in the fourth sequence that we examined, we saw that the recursive sequence a0 is equal to 2, and subsequent terms can be found by taking half the previous term plus 3. We saw that this sequence was monotone, it was increasing, and it was bounded between 2 and 6. So, note that this sequence is monotone, it was increasing, and bounded. That means the monotone convergence theorem is unlocked. And we can safely conclude that the sequence must converge to something. So the question is, can we find out exactly what the sequence converges to? Can we calculate the sequence's limit? Now, looking back at the terms in the sequence, I suspect that the limit of the sequence is 6, because in our calculations we can really see these terms getting closer and closer in value to 6 as the index n increases. But in case the limit of your sequence is something that's kind of strange, in case it's something to do with e or a square root and it's harder to know what the limit is exactly just from looking at it, I would like to show you a process that can be used to find a limit of a recursive sequence like this one. Process. To find the limit of a recursive sequence. So the first thing that we're going to note is that the limit of a sequence doesn't depend on what you choose to be the first term in the sequence. an minus 1, and in general an minus whatever. No matter where you start in the sequence, the limit is always going to be the same. The limit is concerned with what's happening when n is basically infinitely large. So the limit is absolutely unconcerned with anything that is happening at the beginning, at the left-hand side of the sequence. The limit only cares about what's happening on the far right, infinitely far right horizon of the sequence. So an minus 1, an minus whatever, all of these have exactly the same limit. So what I'm going to do is I'm going to take the recursive equation an equals 1/2 an minus 1 plus 3, and I'm going to apply the limit as n goes to infinity to both sides. So on the left-hand side, I'm going to write the limit as n goes to infinity of an. I'm going to write the limit as n goes to infinity of 1/2 an minus 1 plus 3. And then I'm going to use the fact that limits always behave really nicely with constant multiples and with sums. So this is equal to the limit as n goes to infinity of an. Pull out the 1/2. And then add 3 to the result. So these two limits, the limit as n goes to infinity of an, and the limit as a goes to infinity of an minus 1, must be the same number. It's the same sequence, it's just that one of them is one step behind the other. On the far right horizon, when n is off to infinity, one step difference isn't going to matter. So let's nickname the limit as n goes to infinity an, which is the same thing as the limit of one step back in the sequence, an minus 1. Let's nickname those both L. And let's remind ourselves that this limit, the limit of the sequence, is what we're trying to find. So back into my recursion equation, I'm going to replace the limit with L. I'm going to replace this limit with L. And lo and behold, I now have a linear equation that can be solved for the letter L. So you can do something really simple. For example, with the limited space that I have left, I can multiply both sides by 2. I can subtract L from both sides, and sure enough, this calculation shows that the limit is equal to 6, as we guessed. The major takeaway here, the key step in this process, is to replace every an minus 1, an minus 2, etc. with L and solve for L. The solution will get you the limit, assuming that the limit does exist. Let's do a practical example of a recursive formula, to do in particular with money. As I've gotten, more mature and I had a real job which paid a real income, I've become more and more concerned with how to store money in a responsible way so that it will actually grow in value over time instead of decreasing in value due to inflation. So recently this exercise has become very near and dear to my heart. So suppose we invest $500,000. You may not have it right now, but as you go and you get your career in engineering, your career in software development set up, you will probably find yourself in this position within the next 10 to 20 years. We invest $500,000 at an interest rate of 8% per year. And each year, after the interest is applied to the account, we're going to go into the investment and withdraw $30,000 to cover our living expenses for the year. Part A, let's try and come up with a recursive formula that will tell you the amount in the account after n years have passed. Alright, so initially when no time has passed, a sub 0, the amount in the account is $500,000. Let's try and calculate how much would be in the account next year after we have applied the interest and withdrawn our expenses. So the first thing that happens is that the interest is applied. The interest being 8%. So I have my $500,000, and then I add on to that 8% of $500,000. After that interest is added on, I go in and I subtract $30,000 for the expenses. So after some cleaning, this is 1.08 times 500,000 minus 30,000. Now in the next year, we're going to do the same process, except instead of working with A0, we're going to be working with A1. So A2 can be found by applying the interest to however much is in my account after year 1, and then taking off what I need for the living expenses. So in general, the formula that I would use is that the amount in year n is equal to add the 8% interest to the amount in the previous year, and then deduct the living expenses. That's my recursive formula for the amount in the account after n years. Follow-up question. This person with these living expenses and with this investment at this interest rate, are they able to live off the interest forevermore? Now we're going to just assume, even though it's not very realistic, that their living expenses remain at about $30,000 for the rest of their lives. Of course, cost of living goes up over time, but it creates a very complicated problem when you involve cost of living, more complicated than we're going to do here. Now, one option would be to try to set an, the limit, as n goes to infinity, of an equal to the limit of an minus 1 equal to L. But this method may not get you the correct answer, because as of this moment, we don't even know for sure whether or not this limit exists. We have not yet checked whether this particular recursive formula defines a sequence which is monotone and bounded. So, before we presume that L actually exists, let's do some alternative work. So the first thing that I'm going to think about is how much interest this investment actually earns from year to year. Let's begin by thinking about how much interest is earned in the very first year. Now on the side, I've gone ahead and calculated that the interest earned in the first year is $40,000, 8% of $500,000. The interest earned in year 1 is equal to this amount, and so the interest earned is greater than our expenses. And as a result, the amount in year 1 is going to be larger than the amount in A0. But as soon as that happens, interest earned in year 2 is going to be even greater than it was before. So the interest earned in year 2 will be even larger than $40,000, which means we will have even more left over when we remove our living expenses. Which means A2 is going to be even larger than A1. And this pattern will continue. We're earning so much interest on this investment relative to our expenses that the amount in the investment just keeps going up larger and larger over time. In fact, if we continue this calculation, we'll probably be able to see that the sequence AN is not actually bounded, that over the course of time the value of the investment will continue to grow and grow without limit. So based on that, not only will the person be able to live off their interest forever, but if they manage to keep their living expenses low, they will probably continue to get richer and richer and richer, even without doing any additional work and making any additional deposits. Alright, of course they're not actually going to live forever. This is just because I'm short on space. They can live off this investment forevermore. Now, based on this reasoning, philosophical question, what's the smallest amount that this person could invest in order to achieve financial independence? They no longer have to work, and they can simply live off their interest forever. And again, for simplicity's sake, we're assuming that the cost of living won't change, even though this isn't very realistic. So, in order for the amount in the investment to remain stable, in order for the amount in the investment not to decrease over time and eventually empty, we need to make sure that the interest is at least enough to cover our $30,000. So if we calculate the interest earned on that first year, initial investment, we need that to be at least as large as $30,000, or our account will begin to drain out and lose value. Which means that the initial investment, in order to be financially independent, has to be at least equal to 30,000 divided by 0.08, which, if I recall correctly, is approximately $375,000. Which is quite reasonable. I guess the moral takeaway is that, first of all, when you do get your job in engineering, in physics, in computer science, and you start to make all of the money, you should start looking into investment opportunities where you can get an interest rate of around 7 to 8%. For example, this is achievable if you invest in the stock market via an index fund. For example, both Fidelity and Vanguard are companies which give you the opportunity to invest in the stock market in this way. It's very safe, very easy, and you make a lot more money than you do storing your money in a regular bank account. Additionally, if you keep your expenses low, if you keep your lifestyle lean and are only spending about $30,000 a year, you only have to be able to save up about $400,000, and you, in theory, no longer have to work ever again, which is a wild thought. For those of you who do take jobs in software development who are earning 6 figures per year, this will be achievable pretty quickly. So bear in mind, a lean lifestyle and a smart investment program will get you a lot of freedom in terms of financial independence. So that's it for today's content. We talked about monotone convergence theorem and what it means for a sequence to be monotone, bounded, increasing, decreasing, and we got some practice checking whether a sequence satisfied those properties. If the properties monotone and bounded were satisfied, then we practiced using monotone convergence theorem correctly to conclude that a series must converge. Then we calculated the limit of a recursive sequence, and we investigated a recursive sequence in the case of a real-world actual investment.